Okay, now we're going to look at rules of factoring. We're going to look at a few examples of each type. So we're going to look at factoring that involves a GCF. We're looking at factoring quadratics, two binomials when the number in front of the x squared is 1 and the number where the front of the x squared is bigger than 1. We're going to look at factoring quadratics by grouping, which will also play into when x is greater than 1. And then we'll look at using the quadratic formula. Look at the difference of perfect squares and the combinations of all types above. So we'll look at a few examples for you to see. Again, just like in the previous one, if you're comfortable with the examples, you can move along and just check your answers at the end. So example 1, factor using the GCF. So look at what the common factor is between both those two terms. And the highest exponent is going to be your common factor. So that's x to the third. When you multiply x to the third into x squared, you get x to the fifth. And when you multiply x to the third into the next term, minus 3 would give you the 3x squared. So when you factor it completely, your result is x to the third times x squared minus 3. Factoring into two binomials when a is equal to 1. Now, just remember when we talk about a, we say that quadratics are written in the form of ax squared plus bx plus c equals either 0, y. In this case, we're using 0 because we're going to find the roots. The roots are when you take the two binomials, and when you set them equal to 0, you solve them using what we call a t-chart, because it kind of looks like a T. And when you solve them, those answers are your roots, or we say our zeros. So it could be roots, it could be the word zeros, it could be solutions. All are synonyms for each other. Now, if you notice in front of this x squared term is a number 1, so that's why we're going to be using factoring into quadratics, quadratics into two binomials when a is equal to 1. This is a fairly common one. What you do is you look at 8 and you say, okay, what are two numbers that multiply to give me 8? And these same two numbers have to add up to give me 6. And you think, okay, well, 4 and 2. 4 times 2 is 8. 4 plus 2 is 6. So this becomes x to the 4, x and a 2. The signs will be the same. That's what this plus sign tells you. If it's positive, the signs are going to be the same. If it's negative, the signs are going to be different. And if they're the same, this is the sign they're going to be. So the middle one tells you what the sign will be. So they'll be plus. If this was plus and this was negative, the signs will be the same and both will be negative. So when I do t-chart here, I get x plus 2 is 0, so x is equal to 2 is one of the roots, and x plus 4 is 0, x is equal to negative 4 is the other root. So the roots are x is equal to negative 2 and x is equal to negative 4. In this example, it's a little different. Notice now that the coefficient in front of x squared is 7. So one technique that we have done in the past is you take the a times the c, so 7 times 10, and you get 70. So you're going to look for two numbers that multiply to give you 70, and two numbers that add up to give you 71. This is one technique to use. Another technique is people usually just do it by guess and check. So you find a procedure that works for you. We're going to use this through this procedure now. It's kind of hard to think of all the factors of 70, but why don't we just talk a little bit common sense? What about 70 times 1? And then 70 plus 1. So you really want to think about what number is fairly close to 71 that would be able to be broken out. Now what we do is we don't write it like we did before with the two binomials. What we do is we rewrite the 71. So you think of this as 7x squared plus 70x, so we take one of the factors, plus 1x. And don't forget the plus 10. Plus 10. And since we're looking to find the zeros, which is the roots, we're going to set it equal to 0. Now we do something called factoring by grouping. You take out the greatest common factor of the first two terms. Notice that the first two terms have a 7 and an x common to them. So when you take out that GCF, you're left with x plus 10. And then notice it should be exactly the same on the other side, or maybe some factoring that would give you that result. And then you really have to write it so that way you see this extra grouping. And you'll say, well, why do I have to write that? Well, you want to now take out this x plus 10 as a factor, and you're left with the 7x and the 1. And those are your two binomials of this quadratic. And then if we do t-chart to solve it, we get x plus 10 is 0, x is equal to negative 10 as one root or 1, 0, and then 7x plus 1 equals 0, and 7x is equal to negative 1, x is negative 1 over 7. So those are your two roots. Some of you may find it much easier to just do this by guess and check. So you would look and see, okay, I have a 7x and an x, and then try to figure out ways to get that answer. That's perfectly fine. A lot of you have your own ways of finding your answers from previous techniques and previous classes. Okay, let's try another example. Notice in this one as well, the number in front of the x squared is bigger than 1, and we're also x to find the zeros. So we're going to use the same technique that we just looked at before. We're going to do 15 times negative 7. 15 times negative 7 is negative 105. So we're going to look for two numbers that multiply to give us negative 105. And then they also have to add up to give us the middle number, 32. So we can think about a few options. We could say, okay, maybe 33 times negative 1, because 33 times negative 1 would give me, if they add up, would give me 32, but we know that's definitely not equal to negative 105. What about 34 times negative 2? Well, that's going to be equal to negative 68. What about 35 times negative 3? Because notice 35 and negative 3 can give me 32. That's negative 105. Bing, 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 bingo. There's our answer. So if it was 35, negative 3, 35, negative 3. So let's get rid of this part here, and let's start with our work. So now we're going to break this up into 15x squared. This breaks up into 35x positive and a negative 3x. Because again, negative 35 minus 3 is 32, and the 7 stays. Since we're finding the zeros, we're going to set it equal to 0. We're going to factor by grouping here. 5 is common to both of them, and an x. When I take 5x from the first, I get 3x. When I take 5x from the next, I'm left with 7. Now notice this is almost exactly the same as 3x plus 7, but it has a negative 1 in it, so take out a negative 1. And then you have two exactly the same parentheses, which is what you want. So when you take out that parentheses, take them out, you're left with 5x minus 1, and that's what you write here. And then you set them both equal to 0. When you set them both equal to 0, let's make a little bit more space here. You're going to get 3x plus 7 equals 0, and 5x minus 1 equals 0. Again, this is called a t-chart. Set both of the roots equal to 0. I subtract 7 to both sides. I get 3x is equal to negative 7. X is equal to negative 7/3. That's one root. Add 1 to both sides. So we get x is equal to 1/5. And that's your second root, or your second 0. So those are your two answers. Again, you could have solved this by guess and check to get to the two binomials, whatever works for you. But this is one technique. Okay, let's look at another example now of factoring, but now we're going to use the quadratic formula. We're going to use the two examples that we have already worked on, example 2 and example 3, and we're going to factor using quadratic formula to find the roots or the zeros, which are the same thing. So remember, our quadratic formula is x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. I recommend that if you have a hard time factoring when a is greater than 1, when the coefficient is bigger than 1, like in example 3, use the quadratic formula because it's going to give you your roots, which is what your goal is anyway. So let's look at example 2 and then example 3, and we're going to use the quadratic formula for both of them. So whenever you do the quadratic formula, make sure the first thing you do is list your A, your B, and your C. So notice that the number in front of the x squared is your A, the number in front of the x is your B, and the number that's without an x term is your C. The next thing I recommend you do is you write your formula. So that way, all you have to do is plug it in. So negative b plus or minus the square root of b squared minus 4ac all over 2a. And then you plug it in. So it's going to be negative 6 plus or minus the square root of 6 squared minus 4 times 1 times c all over 2 times 1. And then you simplify it. So x is equal to negative 6 plus or minus the square root of 36 minus 32 all over 2, which is negative 6 plus or minus the square root of 4 all over 2. And you need this plus or minus here because now you're going to get two answers. So you're going to get x is equal to negative 6 plus, remember the square root of 4 is 2. So 6 plus 2 all over 2. And then x equals negative 6 minus 2 all over 2. This gives you a negative 4 over 2, which is a negative 2. And this gives you a negative 8 all over 2, which is a negative 4. So your answers are x equals negative 2 and x is equal to negative 4. If you remember, those are the two numbers that we had earlier when we solved for this expression. Okay, let's look at the second one. Again, your A, your B, your C. Whatever sign is in front of the A, B, or C also stay with the terms. Write the formula. Okay, and we plug them on in. So x is equal to negative 71 plus or minus the square root of b squared, so 71 squared, minus 4 times 7 times c all over 2 times 7. When you plug this in, you get negative 71 plus or minus the square root of 71 squared, which we'll figure out in a moment, minus 4 times 7, which is 28, 28 times 10, so 280, all over 14. So then we find out what 71 squared is. We plug that in our calculator. And we get 5,041. And you subtract 280 from that. So you're going to get x equals negative 71 plus or minus the square root of 4761 all over 14. And then we take the square root of that answer. So we get negative 71 plus or minus 69 all over 14. So we get two answers. Negative 71 plus 69 all over 14. And negative 71 minus 69 all over 14. So we get plus 71 or negative 71 divided by 14. So this gives us 10. And then you have negative 71 minus 69 all over 14. We get negative 10. I think I made one little error there. So negative 71 plus 69. And then this gives us, this one was a mistake here. So when I plug this in my calculator, I got negative 0.142. When I round to the fourth decimal place, I get 1429, which is negative 1/7, which is exactly the same answer we got before. The next example we're going to do is factoring by grouping. We did this in some essence in the examples that had a is greater than 1. So what you want to do is you want to look for parentheses and GCFs that are common so you can regroup. So notice that if I look at the coefficients, what's common to both 10 and 12? Well, 2 is, right? So I can take out a 2. What's common to both 2x plus minus 3? Notice that they are common to both of them. So you take out the highest exponent. Sorry, take out the lowest exponent. So that'd be 4. And the same thing here, the lowest exponent is the 2. And then what you do is you leave everything else in here. So you're going to have 2 times what gives you 10. That's going to be 5. Then you write the parentheses. And you say, okay, all of this was taken out here because it's got the 4. So you don't have to have anything there with 2x minus 3 because the whole group of that was taken out. But when you look at the 4x plus 1, the square was taken out. So that means you're still left with one of the 4x plus 1's in there. So remember, when you multiply like bases, you add exponents. So it gives you the 3. Then you keep your plus sign. 2 times what gives you 12? That'd be 6. Then you look at this 2x minus 3. It has the 5, so it needs the 2x minus 3 to the 1. And then the 4x plus 2 squared is completely taken out. So this would be your grouping result, but you can simplify this, and you should. So you get 2x minus 3 to the 4th, 4x plus 1 squared. When I distribute the 5 into this binomial, I get 20x plus 5. When I distribute the 6 in, I get 12x minus 18. And then just combine that. So you get 2x minus 3 to the 4th, 4x plus 1 squared. This becomes 32x minus 13. Example we're going to work with is a difference of perfect squares. So in order to use this technique, you have to have a subtraction symbol or difference between two terms, and the two terms have to be perfect squares. So notice that this is 16, that's perfect square, and so is x squared, a perfect square. Similarly, 25 and y squared are perfect squares. So you can only use this technique presented here if you're given this situation. So let's give it a shot. What you want to do when you have the difference of perfect squares is you want to get two binomials again. And what you do is you take the square root of the first term, which will be 4x, and you put that in the front. Wherever this term is, it fits in the first space. It also has to then go in the first space of the two binomials. Similarly, the square root of 25y squared is 5y. And then you just put two opposite signs in there. Remember, this is like what we worked with the conjugate, because when you multiply a term by its conjugate, the o and the I of the FOIL disappears, so you're left with just the square of the first term minus the square of the last term, which is what we have here. So difference of perfect squares is really nice because you don't have to think too much. You just got to take the square root of the first and the square root of the second and write them in two binomials with two different signs.